Hey everybody, Dr. A here, and in this video we're going to be exploring an example of drawing shear and moment diagrams using the graphical method. So let's go ahead and get started. So to start, we're being given the following. We're being told to use the graphical method to sketch the shear force and bending moment diagrams. Now here what we have is a simply supported beam with a cantilever overhang. All right, so if you remember, a simply supported beam is one where you have an external hinge like we have at A and a roller like we have at B on opposite ends of the beam. Well, when you have a cantilever overhang, one of the ends of the beam is going to have a little overhang segment. So that's what we have here with BC. All right, so our beam has that external hinge at A, and then we have a 20-foot length where we have 150 PLF uniform load over that 20-foot length. Then we encounter a roller at B. Then we see the 6-foot overhang, which has a 500 pounds applied load at the free end. All right, so to get started with the graphical method, the first thing we're going to do is solve for external reactions. Now, we should be pretty comfortable with solving for external reactions by this point, so I've already written out the work for it. I'm going to talk us through it, but I'm going to move through it pretty quickly so we can actually get to the shear and moment diagram part of this example. So to solve for externals, we're going to draw a free body diagram of the entire system. So you see at point A, we have a vertical reaction AY and a horizontal reaction AX. AX is 0 because we have nothing applied in the X direction. At B, we have a vertical reaction BY, and then we drew the dimension lines here in the applied loads. So to solve for these externals, the first thing I did was I said, let's take the sum of the moments about this point B. And so I started with AY times 20 feet, and there's a negative in front because AY is causing a clockwise rotation about point B. Then I said plus 150 PLF times 20 feet times 10 feet, and then minus 500 pounds times 6 feet equals 0. I solved for AY to get 1,350 pounds going up. Next, I said, let's take the sum of the forces in the Y direction equals 0. And so here I said 1,350 pounds, that's the AY, that's pointing up here, minus 150 PLF times 20 feet, plus BY, minus 500 pounds equals 0. And then we see that BY is 2,150 pounds going up. So there's my externals. Again, we should be pretty comfortable with this. So now let's get to the part where we're actually drawing the shear and moment diagrams. So whenever I use the graphical method to draw the shear and moment diagrams, what I like to do is first redraw the beam itself. So I'm going to do that here, and I'm going to go ahead and draw my reactions here. So we know that AX was 0, AY is 1,350 pounds, and then BY over here is 2,150 pounds. And then we have our dimension lines here. So that's 20 feet, 6 feet. And then I'm going to go ahead and draw the applied loads that were given to me. So that's 150 PLF, and then this is the 500 pounds. So what we've drawn here is what we sometimes call the loading diagram. Okay, this is all the loading, including the reactions on the beam. The next thing I'm going to do is draw my shear force diagram axes. Now, when you're first learning this, it's good practice to do this in a very organized fashion. So what I'm going to do is I'm going to sketch my shear force diagram axes just like this. I'm going to sketch them directly below my beam loading diagram, and I'm going to label my axes appropriately just like this, okay? Now what I'm going to do is I'm going to show some intermediate calculations over here in this kind of blank space on the right side. Again, when you're first learning this, it's a good idea to show some intermediate steps along the way. And once you get fast at it, you can then maybe do more things quickly in your calculator without showing as many calculations. I'm going to show the calculations in a little bit more detail for this example since we're kind of learning this from scratch, okay? So the first thing I'm going to do, remember this is shear force diagram, so this is the force that is parallel to the beam's cross-section. The first thing I'm going to do is I'm going to say, okay, moving from left to right, I'm going to start on the left side, move from left to right. As I move from left to right, what is causing a slicing effect through the beam's cross-section, okay? So if you notice, the first thing we're going to encounter is this 1350 pounds. This is going to be the first force that causes a shearing effect through the beam's cross-section, okay? So I'm going to say, I'm going to make some notes over here. I'm going to say at x equals 0, the change in shear is 1350 pounds, okay? And so what happens is, in my shear diagram, I'm going to start at 0 and I'm going to jump up, okay? I'm going to jump up by an amount equal to 1350. Let me write that a little bit better. 1350, okay? Now, also at x equals 0, since I've jumped up by 1350 pounds, the shear force is, of course, 1350 pounds, okay? Now, what do we do next? Well, we're going to ask ourselves, okay, what is happening on this domain from 0 to 20 feet, okay? From 0 feet to 20 feet, we have this uniformly distributed load that's pointing down, and that's going to cause a slicing effect through the beam at any given spot along that domain, okay? So here's what I'm going to write next. I'm going to say from x equals 0 to x equals 20 feet. What's happening? Well, I'm going to have a change in shear equal to what? Well, if you remember from your background information, the change in shear is equal to the area beneath the loading diagram, okay? So the change in shear over this domain is going to be equal to 150 PLF times 20 feet, okay? So that is the area of this load diagram where the length of the load diagram is 20 feet and the height of the load diagram is the 150 PLF. So it's the area of this rectangle, okay? Now it's pointing down, so we're going to put a negative in front of this. So that means the change in shear from 0 to 20 feet is going to be equal to what? Well, it's going to be equal to negative 3,000 pounds, okay? So that means the shear force has changed. That's delta V. It's changed in the negative direction or the downwards direction by an amount equal to negative 3,000 over this length. And it's done so in a uniform fashion, all right? So what does that mean for us? Well, that means that at x equals 20 feet, just to the left of that 20-foot mark, so I'm going to use some mathematical notation and put a little superscript negative sign there. That means that the shear force is going to be equal to what? Well, we were at 1350, and then over this 20-foot length, we dropped down by 3,000. So I'm going to say that's 1350 pounds minus 3,000 pounds. So that shear force just to the left of 20 feet is going to be negative 1,650 pounds. So that's going to be about right here, okay? So negative 1650, okay? So what we've done is we have, going from left to right, we've popped up by 1350. That was the AY reaction. And then this uniformly distributed load has pushed us down at a constant rate down to this value here, okay? Draw that a little bit better for us, right there, okay? Now, this is linear. Let me change colors here. This is linear, okay? And guess what the slope is? The slope is 150 PLF, okay? well, negative technically, negative 150 PLF, so put a little negative sign there. So that means that our slope of this linear portion of the shear diagram is the intensity of the load, okay? So we have now landed infinitesimally to the left of that point B, of where BY is. We're just to the left of B, which is why I have the little superscript negative here, okay? So what do we do next? Well, next we encounter BY. That's the next thing that we encounter as we move from left to right. So we're going to say at x equals 20 feet, we say the change in shear is equal to BY, which equals the 2150 pounds. And it's pointing up, okay? So what does that do to our shear diagram? Well, that pushes us up by an amount of 2,150 pounds. That's why we call it the change in shear, okay? So then that would mean that specifically at x equals 20 feet, just to the right, what is the shear force going to be? Well, it's going to be this negative 1650 plus 2150, okay? Negative, here, let me write this a slightly different spot so I have more room. Let's say shear force is negative 1650 pounds plus 2150 pounds, which should land us right at positive 500 pounds. So that's going to pop us up to about right here, okay? Maybe make it a little bit lower right here. That's a positive 500 pounds, okay? Now, look at the notation here. This is at x equals 20 feet just to the right. So when we were at the left of B, we were at negative 1650. Then we encountered BY, which is at 20 feet. That pushes us up by an amount equal to the 2150. And now we are infinitesimally to the right of point B, which is 20 feet with a plus sign, and we are at 500 because we said negative 1650 plus 2150, 500, okay? What happens next? Well, if you keep moving left to right, you see there's nothing new happening on that 6 foot length. No new loads are being applied there. So I'm going to keep this constant. Straight line, horizontal line, because nothing is happening, all right? Now what happens? Well, we're going to scroll down just a little bit. I'm going to say at x equals 26 feet, we encounter a change in shear of negative 500 pounds, okay? That negative 500 pounds is this applied load, okay? And so what happens when we encounter that? Well, we're going to get pushed down back to 0, okay? Because we're going to say that the shear force is equal, this is at 26 feet, the shear force is 500 pounds minus 500 pounds, which is 0, okay? And from here we have this shear force diagram, okay? So the first part of the diagram is linear with a slope that's equal to this distributed load, negative 150 PLF. And then in the second part of the diagram here, the slope or the diagram is constant and the slope is 0. All right, so that's our shear force diagram. What about the bending moment diagram? Well, I'm going to scroll down a little bit and I'm going to stack my bending moment diagram beneath my shear force diagram. All right, so re-sketching some set of axes here, I can start drawing my bending moment diagram. Now remember, the bending moment diagram is going to be developed by looking at the area beneath the shear diagram. Okay, remember, at this point, we're looking at the change in moment. The change in moment, delta M, is going to be given by the area beneath the shear diagram segments. All right, so these are pretty simple shapes, But the thing is we need to get the dimensions. We notice that we have a lack of symmetry here. This point right here where the shear is 0 is not at 10 feet. It's not right in the middle. It's a little bit to the left, okay? So what we need to do now is use similar triangles to figure out what are these dimensions here, okay? So I'm going to do that. I'm going to call this dimension A, and then I'm going to call this dimension here 20 feet minus A, okay? And I'm going to use similar triangles with these two triangles. They're similar because they share a common angle here and here. And I'm going to solve for these dimensions A and then 20 feet minus A. And the reason why I need that is I need to be able to calculate these areas, all right? So I'm going to do that in green, and I'm going to do it in this kind of open space here just so I don't have to scroll as much. So I'm going to say A over 1,350 pounds equals 20 feet minus A over 1,650 pounds. And I'm going to do a little bit of rearranging here. We can rearrange this and solve for A. I'll show one intermediate step. I get 1.222A equals 20 minus A. Do a little bit of rearranging, and I get A is equal to 9 feet, and I get 20 feet minus A equals 11 feet. Okay, now again, I just showed my work right here in what used to be an empty space just to minimize me scrolling around. If you're writing notes right now, you can put this, anywhere off to the side. Okay, so I'm going to follow a similar process that I did with the shear diagram, except I'm going to do that by generating the moment diagram, looking at changes in moment. All right, so the first thing I'm going to do is I'm going to say, what's the change in moment from the beginning of the beam up to this point A, which is at 9 feet. All right. Well, the first thing I'm going to notice is my moment at point A is 0, right? We had an external hinge at point A, and so there's no moment there. So that's going to start at 0 at this particular spot. All right. Next thing I'm going to do is I'm going to say from X equals 0 feet to 9 feet. All right, that's where we have a 0 shear. I'm going to say the change in moment is going to be the area of the shear diagram, 1/2 times 1,350 pounds times 9 feet. Okay, that's literally this area. 1/2 base times height is the area of a triangle. And so that change in moment is going to be equal to 6,075 pound-feet, okay? And so that's going to put me, let's say, about right here, 6,075 pound-feet, all right? Now, how are these 2 points going to be connected? Are they connected by a straight line? No, okay? This is going to be parabolic. Why is that? Well, remember, the moment diagram is generated by taking the integral or the antiderivative of the shear diagram, okay? So what is the integral, or what is the antiderivative of a linear function? Well, it would be quadratic, which means its plot is parabolic, all right? And specifically, if you have a linearly decreasing slope here, your parabolic arc is going to be concave down, all right? So there's the 60/75, all right? Now, what about on the next part of the domain? Well, we need to find this area here. This is another triangular area, except it's negative now, all right? So next thing I'm going to say, well, first I'm going to say the moment at X equals 9 feet is the 60/75 pound-feet, because I started from 0, all right? Now I'm going to say from X equals 9 feet to 20 feet, the change in moment is going to be 1/2 times what? Well, times the negative 1650, and then times this distance, which we figured out was 11 feet a few minutes ago. So negative 1,650 pounds times 11 feet. Okay, so that gives us a value of the change in moment of negative 9,075 pound-feet. Now, that's a change in moment, okay? That means that in order to get the moment that is happening at point B, we have to combine that with the moment that we just previously got. So I'm going to say next, at x equals 20 feet, the moment is going to be 6,075 pound-feet minus 9,075 pound-feet. And so that will get us a value equal to negative 3,000 pound-feet. All right, so that's going to take me down to about right here. That's negative 3,000, okay? And again, this is still part of that linear segment that's decreasing. So that means that I'm going to have this is going to continue to be concave down. Let me draw that a little bit better for us. Okay, so one more time. There we go. It's as good as it's probably going to get with me freehanding it. So that's a parabolic arc, and remember, this represents the antiderivative of this linearly decreasing segment here. All right, almost done now. What do we do with this next little segment here? Well, we're going to say, I'm going to do some scratch work over here in this blank space so I don't have to scroll as much. I'm going to say from x equals 20 feet to 26 feet, the change in moment is equal to what? Well, it's going to be the area of this rectangular segment here. So that's going to be 500 pounds times 6 feet, which is a positive 3,000 pound-feet. So then what will be our moment at x equals 26 feet? Well, our moment is going to be where we were at negative 3,000 pound-feet, and then we add to it that delta M we just calculated plus 3,000 pound-feet, which brings us back to 0, okay? So that means that our moment here is going to be 0. Now, how are these two points connected? Well, this is connected by a straight line segment, okay? Now, why is that? Well, think about it. What is the antiderivative or the integral of a constant, a positive constant function? It is a linearly increasing function, okay? So we'll make some notes here. We're going to say, you know, this is concave down quadratic, and this segment is linear increasing, all right? And I like to shade my diagrams in, and that becomes our moment diagram. So one more time, whenever you have a linearly decreasing shear diagram segment, that will result in us having a concave down quadratic or parabolic moment diagram. And then here we have a positive constant shear segment, which results in us having a linearly increasing moment diagram segment. Okay, so that concludes this example. And again, once you get fast at this, you won't need to show all of these calculations in all of your work here. You could do a lot of this quickly with a calculator, but again, for the purposes of understanding and learning, I showed all of these intermediate calcs to make sure we know how to generate this. So that concludes this example. If you found this video helpful, please hit like and subscribe. Thanks for watching.